we're going to learn something different, and we're going to use still a continuous outcome variable. Remember that in all of these modules of analysis that you're going to learn, we're only going to focus on an outcome variable which is continuous. But having said that, your predictor variables can vary. Your predictor variables can be all continuous. If it is an all continuous, then you learned you can use multiple linear regression, which is a rather not so difficult to conceptualize because you'll have scatter plots to deal with. But as I said, I mean, in real life, in real data analysis situation, you will need to use both continuous as well as categorical predictor variables. Sometimes you will convert from a continuous to a categorical predictor variable. So how do we mix this, and how do we make sense of those things? This is the objective of conducting what is known as an analysis of covariance. So we will be using a continuous outcome variable and a continuously distributed explanatory variable plus a categorical variable, and we'll see how the relationships change over the different categories of these variables. Okay, so this is what we're going to learn in this particular module. So here we've got a challenge. The challenge is this, that we've got some quantitative variables like continuously distributed variables or continuous variables, and there are some variables that are often referred to as qualitative variables or categorical variables, and these variables have got different categories or levels. For example, gender, male, female, or for example, ethnicity. Okay, Indians, non-Indians, or within the Indian ethnicity or religion, for example, Hinduism, Islam, Christianity, etc. So these, you get a drift. That is, you're dealing with, on the one hand, continuous explanatory variables and categorical explanatory variables, and we want to put both of them together. Up till this far, using our software, if you were to follow this series alone, you'd be well advised to use only continuous explanatory variable. But this time, we're going to take a look at what is known as a analysis of covariance, where we'll see one variable is a continuous, the other is a categorical, and they will all covary with the outcome variable. Here we'll learn the new thing that we're going to learn in this is known as dummy coding, and the technique that R uses in dummy coding in this context is known as treatment coding. So we'll learn a little bit about that, and we'll learn how to interpret the linear model data with this. So the preliminaries, for example, is this, that we're going to apply whatever we learn here to those situations where both continuous and categorical variables are important predictors of an outcome variable. As I explained, if you have got length of stay as a variable and you've got two different explanatory variables, one being, say, gender, the other being, say, a dosage of a certain medication, then that would be an example of this. Another example, you have already met this, the blood creatine phosphokinase levels, and we kind of try to explain that using blood body weight and the different age groups. So, or maybe blood cholesterol levels or some other things. So, moving on to this, general motive. So y is the outcome variable, beta 0 is the intercept term, beta 1 is the regression coefficient for the first variable x1, beta 2 is a regression coefficient for the second variable x2. But here is a second variable, which is x2 has got is a qualitative variable with one or more levels, as we see. So, for example, consider that we were to model, creatine phosphokinase variable. So let's say that the creatine phosphokinase in athletes of various age groups and their body weights. And we say that, okay, our main area of interest is what is the relationship of creatine phosphokinase in athletes with weight. So if per kg increase in body weight, for example, what is the extent of the change in urine CPK concentration? And is it different for people with young age and old age, and what it's going to be like? So we say that if you're young, your age is less than 35. If you are older than 35 years, then you're 1. So we divided age into 2 categories. That's the simplest that we can get. And you will get the drift that you can use this combination in other categories and other levels as well. So when we do this, it becomes a bit complicated because you can either have the same regression line for both groups. So we'll say that the association between age and or the association between weight and CPK is kind of similar. That association is similar. But the trajectory is going to vary depending on whether you are an older person, that is more than 35 years, or a younger person, less than 35 years. So that is different. So same regression line for both groups. And the same regression line for both groups where, we don't really care much about that. So we'll say, I don't care about your age distribution. I will just go with whatever is a regression line between weight and creatine phosphokinase. Simply you use beta 0 plus beta 1 times x. And that's not very, 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 very informative, is it? So we'll say, okay, let's fit some separate regression lines. In this, the slope remains the same. Think about it. The slope basically tells you is that with each increment in the body weight, what is the increment or what is the change in the creatine phosphokinase? For both men and women, that slope will remain the same, but maybe for men or for both young and elderly, the age will remain the same. Young and old, the age will remain the same. However, for the older group who are given a value of 1, that line will be shifted by an x distance. Okay? So we'll have 2 different lines. So then we say that it's going to shift by B0, which is the intercept. That intercept will get shifted or changed. It can be even more complicated. So let's say there is actually an interaction between the age band, that is maybe the elderly for a specific weight have got a different association than the younger people with this. So then we have got a little bit more complicated where the slope itself is going to be different depending on who you are. Okay. So in the first case, when you have got something like B0 plus B1x plus B2d plus B3x times d, so when d actually becomes 0, we have got B1x. But when d becomes 1, then it becomes something like B0 plus B3. So B3 is added to the slope of x. The slope changes. And then on top of that, we'll have some effect for B2 itself, because B2 is where we find that difference here. So this becomes a bit of a complicated issue. So let's take a look at it and then we can have some sense. So as we said, the first thing is to take some plots out. So here's a plot. So that plot CPK, we plot we have removed the observation number 11 because we saw that that observation was kind of an outlier. So we wanted to make things really simple. And we just want to use plot. We want to use the CPK, CPK by weight. Note here the difference. Earlier, or in previous modules, when we wanted to plot something like this, we used the the formula. And that formula kind of served us well, because in the formula, the y-axis was first and followed by the x-axis. In between, we put a tilde mark, and that kind of worked well. Here, when we put a plot like this, more traditional, we are extracting the weight variable from the dataset.cpk, and we put the x first and then the y, and then we plot it. And R is intuitive enough. As you can see, R will tell you that, look, we are going to only get a scatter plot. Then we do something that is quite interesting. We are fitting a regression model, and we are fitting the regression model with a linear model, or we're fitting it with a non-linear model. That is, we're fitting it with an interaction term. And then what we're doing is we are working on that model on the basis of the fact that we are using, to keep things again simple, we are just fitting in two lines, and therefore we see AB line, two lines without the interaction term. We could have fitted the interaction term, and I'll leave that as an exercise to you. So we fit that to you. So let's take a look at where do these numbers like minus 755.92 and 17.53 and 92.63 and 17.5, they come from. They come from here. So here is the output for the interaction case, and you can see that the interaction case is somewhat different. Very similar outputs, exactly everything that we had seen before. You see that the only variable that is really important is the weight. Now note in the third line something that is very, very interesting, and that is it says age rake 35. Now, where does that come from? Remember, when we recoded the age, we recoded the age in a way in which age band 35 and above was given a value of 1, and the age band that was less than 35 years was given a value of 0. So here what R is trying to tell us is this, that as if that age band was converted into a continuous variable with 0 as the reference category and whatever else remained as the category on which it's going to give you some values. So rather than having it at 0, they'll say age at 35 years and above given a value of 1 is presented here. So it kind of reverse coded that 1 and gave you back that age, age recoded at 35 years above is what we're going to find the beta for. And then what it did was this, that it kind of put also the interaction term. So weight colon age range 35. You can obviously see that for the reference category it would have weight times age range at 0 as the one age recorded at 0 as a reference category. So you see that what it is like. When something like that happens, you see that this is how they got presented, and we could go with our usual ways of getting about them by plotting these numbers and fitting these, etc. But to keep really things as simple as they could be, we then put the output for the non-interaction case, and here you can see that it just merely puts the weight and the age more than 35 years, or equal to or more than 35 years. That is the category 1 here. Once more, you see that when dichotomized like this, age does not become statistically significant. Of course, it was not, even when age was treated as a continuous variable. But you see that the weight is statistically significant, and you can see that this is important. So after this, what we did was that we plotted the two lines. Now, one plot, of course, came from the fact that we had to include an intercept term. So the intercept term and the weight was what was important. So we put that in there. So let me show you the non-interaction case graph. That'll make some sense. If you remember from the previous equation, The solid line plots the interaction term and the beta for weight alone. And you can see that there is a steady line going by that. We knew that age was not significant here. It's not really something that was really important here. But if we put the age in there as well as a linear model, then we see that in the linear model, of course, the intercept went down further because it was deducted further by something like 92. And age, of course, at 1 kind of then had very similar relationship with the weight with the CPK. And this is kind of theoretically driven because we reasoned or we rationalized that there is no real reason to think that the age and weight were interacting in this particular case. So we just left it that it is that. So one of the things from here on is a very natural question as to why was age treated like that and what does that mean? We introduce a new term here known as dummy coding of a variable. For k-level predictor, we need k-1 dummy variables. In our case, we had age as 2 levels. Age more than 35, which was given a value of 1, and age less than 35, which was given a value of 0. When we presented that to R, and we asked R that R in an ANOVA circumstance, we would like to analyze the data, R took those 2 levels and created 1 dummy variable. So instead of age rec being treated as, a variable with 2 levels, R automatically converted that into an age rec 35 that represented 1 and the remainder was 0. We could have divided the age into 3 bands, perhaps less than 20, between 20 and 35, and 35 years or greater. If this was the case, then R would create 2 variables and would have given us that kind of an answer. So those 2 variables would be known as dummy variables for that one variable, for that one categorical variable. And there is a, there are different ways in which R treats everything. There is one way of coding which is known as treatment coding, where the first level is assigned the value of 0. So in this case, the level was less than 35 years. That is assigned the value of 0. Or whoever is the lowest level, that would be assigned the value of 0. And only one level will be assigned the value of 0. The rest of them will be assigned a value of 1 and 2, and subsequently it will go up. R specifically assigns levels in a factor alphabetically. So for example, if you have got religion, and if you had like Hindus and Muslims, then R would start assigning values 0 to Hindus and 1 to Muslims. If you had Hindus, Muslims, and Christians, Christians would be assigned a value of 0, Hindus 1, Muslims 2. Of course, if you want to play with R, then you can change the names of the levels and R will accordingly adjust what value it is going to assign to that particular level or category. And in R, the coding that it uses for dummy coding is treatment coding. Okay. So we have seen an example with 2-level variables. So to make things a little bit clearer, let's take a look at an example where we look at ANOVA with 3 levels of explanatory variables. In here, it was like the data came from Sir Cyril Bart's data on IQ of twins raised by either natural or foster parents. And we would like to test the IQ of these twins to see whether they were influenced, or we wanted to kind of explain the IQ of children raised by foster parents by the IQ of their biological parents as a function of their social status in which they were raised. Could be upper, middle, or lower. And so how would that work? Here is a code to start with. There's a library again. It comes from the faraway library. The data is called twins. As usual, the first thing that we do is we plot the biological and the foster parents, and we'll see how do they look like, and then we'll use the twin LM, which is the linear model, and we see that we are using an interaction term here. So the IQ of children raised by foster parents as a function of the biological times their social status. The data are twins data, and we print the summary. Here is a regression output. In the regression output, you can see that we have put an intercept term, which is not at all significant, so we can probably take it out. Biological IQ is a very strong predictor of the IQ of children raised by foster parents, which means that the IQ of the children raised by their biological parents very closely corresponds to the IQ of the children raised by their foster parents. And again, you can see that of the three categories of the social class, the low, middle, and the other ones, you can see that the low, middle, etc. are given their own codes, and accordingly they've been dummy coded. Okay, so so the low is given the value of 1, the middle is given a value of 2, and another one could have been given a value of 0. So we could see how these things have worked. But you can see that the social class didn't really matter in this as much as we can see here. Okay, so the only thing that really mattered was the biological parent raised, and that kind of explained it. And the model is statistically significant, and it explains about 75% of the variability. If you go to the scatter plot without regression lines, then you can see that there's nearly a linear things, and I have not really drawn the fit lines here. Also because the fit lines would not give you much more information, but I would leave you as an exercise to go and fit the lines and see what sense you make of it. I've already given you the codes before. But whereas we are now interested is to see whether a linear model fits better or whether an interaction model fits better. So what is a linear model? The linear model is just a sum of the biological and social, and the interaction model is biological, social plus that. Okay, and we make these comparisons by using the ANOVA, twin LM, twin LM2, and followed by the steps. So then, if we put them together, this is the code that we do, right? So we took the twin LM2 with biological plus social, which is an additive model. And the third model is where we only put the biological. Is the biological model alone better? Is the biological plus social model better? Okay. Is the additive model better than the biological model alone? Okay. So we do it in two ways. One is the analysis of variance tables, and the other is with the other one. And what is really important here is then we'd like to see whether what happens when we add biological parameters to it. So in the first model, we are looking at the biological times social, and the second one where we're going to take a look at the biological plus social model. So now
when we add those terms, we see that it is not necessary that a biological model alone is going to be very useful. So the first one, where we're going to have a multiplicative model versus an additive model, we see that there is virtually no difference of adding, of taking out the biological times social. The interaction term didn't matter. Also, adding the social term did not seem to matter here again. Yeah. On the other hand, if we were to keep the biological and social and then take out the social component of it, as you can see, comparison of the models on the right hand side, you see that the Akai key information criterion at 112.35 is lower than if we took out the biological model, which is 151.9. So which means that probably a social model is adequate or a biological model adequate. And that's the reason why I said that it doesn't make much of a difference, because as you can see that it is not so much as the absolute values of your Akai key information criterion, but it's more around the changes. So when you remove the biological model, for example, you see the Akai key information criteria lips to about 150.98. So which means leaving the biological model there, biological variable, would be perhaps a better ploy. So we see that here when we compare the models, we see that the biological parenting probably explains most of the foster IQ, children raised by the IQ by the foster parents. So the importance of this is this, that you can see that by using these different kinds of models and modeling strategies, you can make comparisons across the models, something that will not be captured by R-squares alone. So as we have seen that the comparisons of the models show that biological parenting explains much of the foster IQs, and ANOVA and AIC estimations from different models helps us to compare the models one with the other. So this kind of helps us to run through the whole run-up of the different types of models. So we've seen that with a given outcome variable which is continuous, we can either have a continuous explanatory variable or a combination of continuous and categorical explanatory variables, which is known as ANOVA, and we can see how changes, how things work. We have seen that R can create dummy variables. We've seen how R creates dummy variables, and we have seen how we can compare the different models together. So this kind of completes this set of slides. Next, we're going to learn how to use analysis of variance, where your explanatory variables are all categorical variables. So till then, happy learning.
So at the end of this few sets of exercises, we have covered a fair bit. In the beginning, you saw that you could work with only two variables at a time, so that made life rather simple. So you had two continuous variables. In simple linear regression, we saw that you could use two continuous variables to explain one with the other. In all cases, the outcome variable was a continuous variable. In simple linear regression, we studied the impact, or we regressed a continuous outcome variable on a continuous predictor variable. In multiple linear regression, we regressed a continuous outcome variable on two or more than two continuous predictor variables. Note that in multiple linear regression, we had one outcome variable that was continuous and two or more than two predictor variables that were also continuous. Now, in the ANOVA, which is analysis of covariance, you had one continuous variable, and your predictor variables could be continuous, and they were all what you call as categorical variables. So a combination of a continuous predictor variable and a categorical predictor variable. So this is where it leaves you that we are going to have a combination of continuous and categorical predictor variables. In the next, we're going to learn what do you do when all your predictor variables are categorical and your outcome variable is continuous. So we'll first learn about one-way ANOVA, and then we'll learn two-way ANOVAs to round it out.